Section 4.4, Newton's Law of Inertia. On Christmas Day, in the year Galileo died, Isaac Newton was born. By age 24, he had developed his famous laws of motion. They replaced the Aristotelian ideas that dominated the thinking of the best minds for most of the previous 2,000 years. This chapter covers the first of Newton's 3 laws of motion. Newton's 2 other laws of motion are covered in the following chapters. Newton's first law, usually called the law of inertia, is a restatement of Galileo's idea. Every object continues in a state of rest or of motion in a straight line at constant speed, unless it is compelled to change that state by forces exerted upon it. Over here in the figure 4.4, looks like the guy yanked on a tablecloth, and the dishes and stuff stayed on the table. Objects at rest tend to remain at rest. Simply put, things tend to keep on doing what they're already doing. Dishes on a tabletop, for example, are in a state of rest. They tend to remain at rest, as is evidenced if you snap a tablecloth from beneath them. Try this at first with some unbreakable dishes. If you do it properly, you'll find the brief and small force of friction are not significant enough to appreciably move the dishes. Close inspection will show that brief friction between the dishes and the fast-moving tablecloth starts the dishes moving, but immediately after the tablecloth is removed, friction between the dishes and tabletop stops them. Objects in a state of rest tend to remain at rest. Only a force will change that state. Let's look at this cartoon. Staying put. A body at rest tends to... Oh no, the dog saw a cat. The dog takes off and exerts a force and yanks the wagon forward. But the kid fell out of the wagon. Why did he fall out of the wagon? Because he was staying in one place and that wagon was being pulled out from underneath him. His inertia caused him to remain pretty much in the same place even though the wagon got pulled forward. Now consider an object in motion. If you slide a hockey puck along the surface of a city street, the puck quite soon comes to rest. If you slide it along ice, it slides for a longer distance. This is because the friction force is very small. If you slide it along an air table where friction is practically absent, it slides with no apparent loss in speed. We see that in the absence of forces, a moving object tends to move in a straight line indefinitely. Toss an object from a space station located in the vacuum of outer space, and the object will move forever. It will move by virtue of its own inertia. Figure 4.5, an air table. Blasts of air from many tiny holes provide a nearly friction-free surface. This is like air hockey. So there's these little pucks. This black surface has a bunch of little holes with air blowing upward out of the holes. And the pucks kind of glide along on a little cushion of air with very, very little friction. We see that the law of inertia provides a completely different way of viewing motion. Whereas the ancients thought continual forces were needed to maintain motion, we now know that objects continue to move by themselves. Forces are needed to overcome any friction that may be present and to set objects in motion initially. Once the object is moving in a force-free environment, it will move in a straight line indefinitely. In the next chapter, we'll see that forces are needed to accelerate objects, but not to maintain motion if there is no friction. Another cartoon, keep on trucking. A body in motion tends to whap, stay in motion. He's trying to stop the truck, but the truck wants to keep on moving because of its inertia. Here are a couple check questions. Number 1. If the force of gravity between the sun and planets suddenly disappeared, what type of path would the planets follow? Answer. The planet would move forward in a straight line in whatever direction it was heading when the gravity turned off. Number 2. Is it correct to say that the reason an object resists change and persists in a state of motion is that it has inertia? Here's the answer at the bottom of the page for number 2. In a strict sense, no. We don't know the reason why objects persist in their motion when nothing acts on them, but we call this property inertia. We understand many things and we have labels for these things. There are also many things we do not understand and we have labels for these things too. Education consists not so much in acquiring new labels, but in learning what is understood, what is not, and why. Here's a sidebar, the link to space science, inertia in action. Pioneer and Voyager spacecraft launched in the late 1970s have gone beyond the orbits of Saturn, Uranus, and Pluto and are still cruising beyond the solar system. Initially, force supplied by rockets sent the spacecraft on their journeys. However, once in outer space, these engines supplied no more force. They were turned off. Except for the gravitational effect of the stars and planets in the universe, do you see that the motion of the spacecraft will continue without change? Next section, 4.5, mass, a measure of inertia. Kick an empty can and it moves. Kick a can filled with sand and it doesn't move as much. Kick a can filled with steel nails and you'll hurt your foot. The nail-filled can has more inertia than the sand-filled can, which in turn has more inertia than the empty can. The amount of inertia an object has depends on its mass, which is roughly the amount of material present in the object. The more mass an object has, the greater its inertia and the more force it takes to change its state of motion. Mass is a measure of the inertia of an object. Mass is not volume. Do not confuse mass and volume. They are entirely different concepts. Volume is a measure of space and is measured in units such as cubic centimeters, cubic meters, and liters. Mass is measured in kilograms. If an object has a large mass, it may or may not have a large volume. For example, equal-sized bags of cotton and nails may have equal volumes, but very unequal masses. How many kilograms of matter an object contains and how much space the object occupies are two different things. A liter of milk, juice, or soda, anything that is mainly water, has a mass of about 1 kilogram. Which has more mass, a feather pillow or a common automobile battery? Clearly, an automobile battery is more difficult to set into motion. This is evidence of the battery's greater inertia and hence its greater mass. The pillow may be bigger, that is, it may have a larger volume, but it has less mass. Mass is different from volume. The pillow has a larger size, which is volume, but it has a smaller mass than the car battery. Mass is not weight. Mass is often confused with weight. We say a heavy object contains a lot of matter. We often determine the amount of matter in an object by measuring its gravitational attraction to Earth. However, mass is more fundamental than weight. Mass is a measure of the amount of material in an object and depends only on the number of and kind of atoms that compose it. Weight, on the other hand, is a measure of the gravitational force acting on the object. Weight depends on an object's location. The amount of material in a particular stone is the same whether the stone is located on Earth, on the Moon, or in outer space. Hence, the stone's mass is the same in all these locations. This could be demonstrated by shaking the stone back and forth in these three locations. The same force would be required to shake the stone with the same rhythm whether the stone was on Earth, on the Moon, or in a force-free region of outer space. The stone's inertia, or mass, is solely a property of the stone and not its location. But the weight of the stone would be very different on Earth and on the Moon, and still different in outer space. On the surface of the Moon, the stone would have only 1/6 the weight it has on Earth. This is because the force of gravity on the Moon is only 1/6 as strong as it is on Earth. If the stone were in a gravity-free region of space, its weight would be 0. Its mass, on the other hand, would not be 0. Mass is different from weight. We can define mass and weight as follows. Mass is the quantity of matter in an object. More specifically, mass is a measure of the inertia or laziness that an object exhibits in response to any effort made to start it, stop it, or otherwise change its motion. Weight is the force of gravity on an object. Let's look at the cartoon over here. Figure 4.8. It's just as difficult to shake a stone in its weightless state in space as it is in a weighted state of Earth. Shaking it back and forth is equally difficult because of its inertia. While mass and weight are not the same, they are proportional to each other in a given place. Objects with great mass have great weight. Objects with little mass have little weight. In the same location, twice the mass weighs twice as much. Mass and weight are proportional to each other, but they are not equal to each other. Remember that mass has to do with the amount of matter in the object, while weight has to do with how strongly the matter is attracted by gravity. Thought questions. Number 1. Does a 2 kilogram iron block have twice as much inertia as a 1 kilogram block of iron? Answer, yes. Does it have twice as much mass? Yes. Does it have twice as much volume? Yes. Does it have twice as much weight when weighed in the same location? Yes. So all those are yes. Number 2. Does a 2 kilogram bunch of bananas have twice as much inertia as a 1 kilogram loaf of bread? Yes. Does it have twice as much mass? Yes. And does it have twice as much volume? Probably not. Does it have twice as much weight when weighed in the same location? Yes. Let's look at what the author wrote for the answer to number 2. 2 kilograms of anything has twice the inertia and twice the mass of 1 kilogram of anything else. In the same location, where mass and weight are proportional, 2 kilograms of anything will weigh twice as much as 1 kilogram of anything. So except for volume, the answer to all the questions is yes. Volume and mass are proportional only when the materials are the same, or when equal masses occupy the same volume. That is, they have the same density. Bananas are much more dense than bread, so 2 kilograms of bananas must occupy less volume than 1 kilogram of bread. Okay, here we are. 1 kilogram weighs 9.8 newtons. In the United States, it is common to describe the amount of matter in an object by its gravitational pull to Earth, that is, by its weight. In the United States, the traditional unit of weight is the pound. In most parts of the world, however, the measure of matter is commonly expressed in units of mass. The SI unit of mass is the kilogram. Remember, SI means the modern metric system. The SI unit of mass is the kilogram. Its symbol is kg. At Earth's surface, a 1 kilogram bag of nails has a weight of 2.2 pounds. The SI unit of force is the newton, named after guess who? 1 newton is equal to slightly less than a quarter pound, about the weight of a quarter-pound burger after it is cooked. The SI symbol for the newton is capital N, and it is written with the capital letter because it is named after a person. A 1 kilogram bag of nails weighs 9.8 newtons in SI units. The mass is 1 kilograms, the weight is 9.8 newtons. Away from Earth's surface, where the force of gravity is less, the bag of nails weighs less than 9.8 newtons. If you know the mass of something in kilograms and want its weight in newtons, multiply the number of kilograms by 9.8. Or if you know the weight in newtons, divide by 9.8 and you'll have the mass in kilograms. Weight and mass are proportional to each other. Weight is equal to mass times the acceleration due to gravity, which is 9.8. Or simply, weight equals m times g, where g is the strength of gravity, which is 9.8 here on Earth. One more check question. The text states that a 1 kilogram bag of nails weighs 9.8 newtons at Earth's surface. Does 1 kilogram of yogurt also weigh 9.8 newtons at Earth's surface? Answer, yes it does. If we want to know the weight of 1 kilogram of anything, we multiply the kilograms times 9.8. So 1 kilogram nails weighs 9.8, 1 kilogram of yogurt weighs 9.8, 1 kilogram of anything here on Earth weighs 9.8 newtons.